Jai Bharat to all students. In last lecture, we have studied some definition related to the graph theory, in which first we have started with vertices and edges. Okay. Then we have discussed walk, path, and cycle. Then also we have discussed loop. Okay. Then in last, Hermitian graph. Okay, so today also we will see the different types of definition related to the graph also. Okay, and it's there. Okay, so we will start with the simple graph. Okay, here for this chapter we have to name any graph or any vertices to some name, to give some of name. Okay, a simple graph, let's say it's a simple graph name as a G, consists of non-empty finite set of V of G of element called vertices. Okay, so in graph there are, let's say, 1, 2, 3 or any number of vertices are there, non-empty. It's not should be not be 0. Okay, or vertices, or you can say nodes or point, and finite set E of G of distinct unordered pairs of distinct element of V of G called edges. Okay, so they have given the name graph as a G, vertices as a V of G, means vertices of graph G, and edges as a E of G, vertices of G graph. Okay, let's assume if we have named the graph as a P, then its vertices should be will be V of P and its edge will be E of P. It's simple as a name. The vertices of graph P, edges of graph P. Okay, so V of G is called vertex set. Okay, in exam you will be asked to write down vertex set. Okay, in last lecture we have only discussed vertices and edges. Okay, but here we have to say that it is a vertex set, and E of G is called edge set. Okay, it is a set of all the edges and vertices available in the graph. So an edge, let's say V and W, it's set to join the vertices V and W. Let's say simple, we have 2 points V and W, and this edge line should be share V and W. So edge VW is set to join vertices V and W, as usually abbreviated to VW. For example, so we have to write down edges like this. Okay, so okay, figure 1.1 here. Okay, vertex set V of G is U, V, W, Z. You have to write down in the set. Okay, U, V, W and Z, and whose edge set consists of the edges. Edges consist of U, V, V, W, W, U and W, Z. Okay, so you have to write down like this. This is only a set. Okay, we have to write down in bracket. Okay, just like this. Set problem, you have also studied a set problem also. Okay, so we have write down graph into a number, a simple set. Okay. Okay, we also have discussed about multiple edges. Yes, this is a multiple edges. Okay, if traffic arises, we will make 2 roads. Okay, so this is a multiple edges, and this is a simple graph. We have studied in last lecture also. Okay, and also this is called loops. Yes, loops means edge joining a vertex to itself. Okay, parking for parking purpose or anything, for road network parking purpose we may allow loop. Okay, so the resulting object with the loops and multiple edge is called general graph. Okay, or simply you can say a graph. But this is called simple graph, and this is for multiple edges and is called only a graph or general graph. Okay, so this is simple with only one edges and no loop, and for the loop and multiple edges we call as a graph. Okay, so you can see that every simple graph, every simple graph is also a graph, but not every graph is a simple graph. Okay, this is not called a simple graph, but this is called also is a graph. Okay, simple graphs means no loops and no multiple edges. Okay, now so we have studied a graph G consists of non-empty finite set V of G of elements are called vertices, and finite family U of G of unordered pairs of element of V of G is called edges. Okay, so use the word of family permits the existence of multiple edges. Okay, for the multiple edges we have to write down as a family. Okay, so V of G is our vertex set, and E of G is also called edge family of graph G. Okay, so we have till now discussed two definition, vertex set and edge family of particular graph. Okay, so figure 1.2 vertex elements is UVW is remain same, but edge consists of the edge UVW, VV twice here, VV twice loop. Okay, VW three times, VW three times, three edges are there, and UW twice, and WZ. Okay, so this is called edge family. Okay, okay, so vertex set, edge family. Okay, and for normal graph we may have called edge set. So there are three definition: vertex set, edge set, and edge family. Both are the same, but we have to write down multiple edges in edge family. Okay, okay, next, isomorphism. Okay, two graphs G1 and G2, let's say there are two graphs, are isomorphic if there is a one-to-one correspondence between the vertices of G1 and those of G2. Okay, we all know what is a one-to-one, and we in function in last semester I think we have discussed function, one-to-one function, one-to-many function, and many-to-many function. Okay, also, so here the what these two graphs are isomorphic if there is one to one corresponding. What is a one to one, and who is the between one to one? It is a vertices of G1 and G2, such that the number of edges joining any two vertices of G1 equals the number of edges joining the corresponding vertices of G2. Okay, so this figure, these two graphs in figure are isometric under the corresponding of. Okay, here you can see that U and I, then X and P, V and M, then Y and Q, W and N, Z and R. Okay, so there are 6 number of vertices in both the graph. Okay, one to one corresponding between both the graph, and edges is also the same. Yes, here you have edges 3 number, also this have 3 number of edges. Okay, also we have 3 number, here also they have 3 number. Okay, all the vertices have 3 number of same edges. Okay, so number of vertices should be same and number of edges should be same. Okay, so this two graph is called isomorphic. Same means these two graph are the basically have same property. Okay, okay, for many problems, the labels on the vertices are unnecessary. Okay, what is the label? Label means we have write down in this figure as a x, y, z and u, v, w. We have give the vertices as a some name u. Here this vertices we have given some name x. Label, we have labeled this vertices as. Okay, for some problem this name or labels is not necessary, so we drop them, and this say that two unlabeled graph are isomorphic if we can assign label to their vertices so that the resulting label graph are isomorphic. Okay, let's say this. Okay, they have not given this name. This is a unlabeled graph. Okay, again a new definition, unlabeled graph. They have we have not given any name to the vertices. Okay, so this is also called isomorphic. Yes, because we have 6 vertices and all the vertices have 3 edges. Here also all the vertices have 3 edges, and number of vertices is also 6. Okay, so now what is the difference between label graphs? This is a label graph and this is unlabeled graph. Okay, let's say difference between label and unlabeled graph becomes more apparent when we try to count them. If we try to count them, okay, let's start with the example, so we will get the better idea of what is the difference between label and unlabeled graph. Okay, for example, if we restrict ourselves to the graph with 3 vertices, we have, let's assume that we have 3 vertices. Okay, so then there are 8 different possible label graphs are available, but only 4 unlabeled graph are available. Let's say example. Okay, this is a label graph. Okay, now we have only 3 vertices. Okay, so we can make the 8 types of graph. Okay, without edges, without 1 2 edges, without 1 3 edges, with with 1 3 edges, with 3 2 edges, with 1 3 and 1 2 edges, 1 1 2 and 2 3 edges, 1 3 and 3 2 edges, and all the edges. Okay, so there are 8 possible 8 possible graphics available for the label if we try to label the graph. But for the unlabeled, we only have 4 possibility, because these 3 graph will in unlabeled will become same. These 3 also will become only one graph. Okay, and this is a different. So there are basically 4 possible available for unlabeled. Okay, so if we count number of graphs available, probability, if you find probability of number of graphic available, then label and unlabeled graphs are basically we have to write down, okay, this is unlabeled or unlabeled, or this is a label. Then we can say that this is a true or false. Okay, so this is a basically difference between unlabeled and label. Okay, next, connected graph. Okay, we can combine 2 graphs to make a larger graph. If 2 graphs G1 and G2 are the and their vertex set is say V of G1 and V of G2 are disjoint. Disjoint means different. Then their union, G1 union G2, is the graph with vertex set of V of G1 union V of G2. We have studied union in the set theory also. Okay, so basically what in graph we will do, we will name only use that this union property. Okay, so we will make the union of vertex set also, and union of edge family also. Okay, E of G1 union E of G2. Okay, so this is a let's say this is a G1 graph AB. If vertices is A and vertices is B and edges is A and B, AB. Union this graph G2. So this will make like this graph. Okay, so if these are not connected, this is also called a one graph. Okay, it's not compulsory to make all the vertices connected to each other. Okay, we can this is also a same graph. If this and also a different graph also, and we want to write down, this is also a same graph also. Okay, so it's not compulsory to that each vertices or each edges should be connected with each other. Okay, so now definition of connected graph and disconnected graph. Okay, graph is connected if it cannot be expressed as a union of graph. Okay, so this is this graph is what is called. Okay, so disconnect graph G can be expressed as a union of connected graph. Each of the which of is called component of G. Okay, so a graph is connected if it cannot be expressed as a union of graph. Okay, let's say this graph G1. Okay, we can not undivide this graph and make it two different graph. Okay, so this is connected graph, this is also a connected graph, but this, it is called a disconnect. Okay, why? Because disconnect, let's say it have not connect with the two graph, and we can make this two graph. Okay, and express as a union of graph 1 union second. Okay, so this is a disconnect graph, this is a whole these two are connected graph. Okay, you get them. So this is they have given this is as a one graph. So this is a disconnect graph. Okay, a disconnect graph with three component is shown in figure. This all are the called as a component. Each of these is called component of G, component of total G. So this is, there are 1, 2 and 3 component. Okay, so this is a one graph and this is called disconnect graph. Okay, and there are 3 component available. Okay, so we have now discussed again two definition, connected graph and disconnect graph. Okay, now when proving result about graph in general, we can often obtain the corresponding result for connected graph and then apply them to each component separately. Okay, so what they are trying to say, well, let's start with example. A table of all the unlabeled connected simple graph. Okay, now they have given combined 4 name. We have studied unlabeled, we have studied connected, we have also studied simple graph. Okay, so they have combined 4 terms, unlabeled, connected and simple graph with up to 5 vertices. Okay, so how many graphics for graphs are we can draw for 5 vertices, and for this condition unlabeled, it should be connected and it should be a simple graph. No multiple edges and loops should be are there. So for one we can make like this, we can make like this for 2 vertices. For 3 vertices we can also make like this for 4 vertices. Okay, so this is our different graphics available for the different types of unlabeled vertices and different edges. Okay, and this is again a 5 type 5 vertices graphics. 11, 12, 13 are all are 5 vertices and different edges. Okay, we can make a different graph. Okay, now if we say we can we have label graph, for this also we can make the 2 or 3 or more label. Okay, let's say 1, 2, 3 and 4 and 5. we can, for this graph also we can make like this: 2, 3, 4, 5 and 1. Okay, so for this also we can make many graph for label graph. Okay, so we for now we have only. Okay, this is a unlabeled graph, example of unlabeled graph. Okay, we can make number of graphics for the given vertices. Okay, so there are basically, you can see that 31 possible for the this particular condition. If they have given label condition, then number of graphics should be no 100 or 200 also. Okay, then simple, if we make only graph, okay, multiple edges. Okay, so this is again a different possibility. Okay, so these are the connected example of connected graph, unlabeled graph and simple graph with up to 5 vertices. Okay, next two definition. One, adjacency and degree. We already discussed degree of vertices. Okay, we said that two vertices V and W of a graph are adjacent. Adjacent means near. Okay, if there is an edge VW joining them. Okay, so these two vertices are called adjacent vertices. Why? Because if they have connected with the edges VW. Okay, adjacent means near. Okay, these two vertices are near. Okay, and also this is a adjacent vertices. Okay, and if we want to say adjacent edges, okay, so we also say that two distinct edges E and F are adjacent if they have vertex in common. Okay, like this. What if they have vertex in common, then E and F are called adjacent edges, near edges. Okay, near. These two vertices are near and they have connected with one edges, and for the adjacent edges they have connected with the common vertex. Okay, also if say again they like say D edges. Okay, so this three also it's called adjacent edges with another. Okay, so adjacent vertices and adjacent edges. Okay, and we already know degree of vertex. So what is the degree of vertex? In last lecture we have discussed degree of vertex V is the number of edges incident with the V. Okay, we have to calculate for particularly vertex. Okay, number of edges are connected with them. Okay, and we return as a degree of V. Okay, and when calculating the degree of V, we usually make the convention that a loop at V contributes to a degree of V. Okay, let's say this is a loop here for V. So we have let's say we have to calculate degree of V. So this is a one edges and this is also a second edges. Okay, so here degree of V is 2, not 1. Okay, we have to calculate loop also. Okay, and a vertex of degree 0 is called isolated. Okay, like we have this see this first, this is a no edges are available, so degree of vertex is 0. So it's this types of graphics called isolated graph, and a vertex of degree of 1 is an n vertex. Okay, this is a n vertex for both the vertices. Both vertices are n vertex. This is n vertices and this is also n vertex. This is not n vertices second. Why? Because they have connected with two edges, so its degree of vertices is 2. Okay, this example is n vertices. This is also n vertices. This is also n vertices. Then Okay, this is also n vertices. This is also n vertices. This 4 is also n vertex. Okay, so again we have studied two new definition: isolated vertex and n vertex. Okay, okay, so we have now studied. Let's revise what are the definition we have studied till now. Okay, we have studied a simple graph. Simple graph means no loop and no multiple edges, and only graph is have consist of loop and multiple edges. Okay, then all the element of in any graph is called vertex set. We have to write down like this in set, in bracket. Okay, so this is called vertex set, and in bracket this is called edge set. Or if it is a multiple edges, then we have edge family. Okay, edge family. Okay, so vertex set and edge family. Okay, if it is as a multiple edge. Okay, then multiple edge is loops, general graph or simple graph. Then we have studied vertex set, edge family. Then isomorphic. Okay, if both are 1 to 1 corresponding with vertices and same number of edges. Okay, then unlabeled graph and label graph. This is unlabeled graph, this is a label graph. Then for the 3 vertices, we have if we count, then we can say that this is a different unlabeled and label graph. Okay, we can, for label graph we can make 8 different graph for 3 vertices, and for 3 vertices we can make only 4 unlabeled graph. Okay, so if we count number of graph is, okay, so we can differentiate between unlabeled graph and label graph. Then connected graph, and how to calculate union graph, connected and disconnect. This is a connected graph, these two, and this two is this graph is a disconnect. Okay, we can make a union. Okay, so connected graph is cannot be expressed as a union of 2 graph or 3 graph. Okay, this is called disconnect graph, and with a 3 component of graph. Okay, it is called component. Okay, so here we have studied 4 different definition: connected, disconnect and component of graph. Then we have make a graph available for 5 vertices: unlabeled, connected, simple graph. Okay, so there are 31 different possible graph we can draw. Then we have studied adjacency, adjacent vertices and adjacent edges. Then we have studied degree of vertices and how to write them, degree bracket v. Okay, then if it is a vertex of degree as a 0, then it's called isolated, and if it is a degree of vertex is 1, it's called n vertex. Okay, again we have seen 2 definition. Okay. Now here is your assignment question. You have to write down vertex set and edge set of this given 2 figure. Vertex set and edge set in bracket. Okay, simple, and upload it in RNWIET application. So now today's lecture is completed.